Radioactivity is something that's talked about a lot.
Now, what you see here is the radioactive dye we injected flowing through your husband's circulatory system.
But doctor, I haven't injected the dye yet.
Good Lord.
Hi.
But what is it really? It starts at the very center of the atom, called the nucleus. Inside of the nucleus, there are two different types of particles, protons and neutrons. Protons have a positive charge, but neutrons have no charge. Neutrons are the source of radioactivity. Usually, the nucleus is balanced between protons and neutrons. Like here, this carbon atom. It has 6 protons and 6 neutrons. However, this isn't always the case. Sometimes there are more neutrons. When this happens, the atom tries to get rid of the extra neutrons to balance it. But where do those neutrons go? They are released, called radioactive particles. There are 3 different types of radioactivity: alpha particles, beta particles, and gamma rays. Alpha particles are the least dangerous. When the neutron is released, it takes 2 protons with it. This makes the atom 4 units lighter and, as it has lost protons, a completely new element. For example, if carbon with 14 neutrons were to release 1 alpha particle, it would become beryllium and go from an atomic mass of 12 to 8. They can be blocked very easily. They can't get through a sheet of paper. Beta particles also tend to be harmless. When they are released, a neutron pulls 1 proton with it and becomes an electron itself. For this reason, the element becomes more positive as beta particles have a negative charge of 1. However, they do not have a significant mass, and therefore the mass of the atom does not change, only the charge and the element. If a carbon with 14 neutrons were to release 1 beta particle, it would become nitrogen, with the atomic weight staying at 12. They can be blocked by a thin sheet of metal, like tinfoil. Gamma rays are the main concern when it comes to radioactivity. Instead of being a product of a neutron being released, gamma rays are energy released in the process and are rarely emitted alone. They have no charge or weight as they are only energy. It takes a very thick layer of lead to block them. Radioactivity can be used to determine how old things are. A process called carbon dating is very common for archaeologists to use to identify this. This is done using half-lives. Half-lives vary from substance to substance. For example, carbon has a half-life of 5,730 years. On the other hand, polonium has a half-life of 138 days. But what does this mean? Say these M&Ms are all neutrons that the atom is trying to get rid of, and each round is the half-life. The first time, it takes a whole half-life to divide them in half. It takes another whole half-life to divide what remains in half. Each time it gets smaller and smaller, but each time the amount it decreases by also gets smaller, until finally there's none left. So how can scientists use this to find age? Scientists find the number of neutrons in the carbon atoms of the artifact. Using this, they essentially do the reverse of the M&M experiment. If we start at round 4 of the experiment, then we know we've gone through 4 half-lives. If it were carbon, then 4 half-lives would each take 5,730 years. 500,730 times 4 is the age of the artifact, which is 22,920 years. That's a long time.